Hi, I'm Craig the geologist, and here's a question for you. How old are rocks? How do we know how old rocks are? Well, that's what we'll be talking about today. Come join me. So the question of how old rocks are is a question that's dogged geologists for ages. In the early days of earth science, back in the 16, 17, 1800s, figuring out how old rocks were, it was really a lot of guesswork. Some people came up with some pretty ingenious methods of trying to estimate how old the earth was and rock units were. One of my favorite methods for trying to estimate the age of the earth came from looking at the rate of salt input to the ocean from freshwater sources like rivers and estimating just how old the earth must be based on the amount of salt in the oceans. Of course, now we know that there's a salt cycle. It's not just a one-way trip for salt into the ocean where it stays forever. The ocean isn't getting saltier. It cycles salt back through the crust through a complex mechanism that we actually talked about a couple of weeks ago. So their estimates based on that were wildly off, and everything they tried gave a whole range of estimates on the age of the earth or age of rock units. These educated guesses were valiant attempts, but they just didn't have the information and the technology to be able to accurately age date rocks. So how do we do it today? Let's talk about that. Let's talk first about relative dating techniques. Now, this is not the way you pick up a cute girl at your family reunion. When I talk about relative dating, what we're talking about is the age of rock units relative to one another. So you're not tagging a rock unit with a specific age. You're not saying it's X years old. What you're saying is, okay, this one's older than that one is younger than this one, that one is younger than all of these, that one's the oldest. That's what relative age dating is. So to that end, we begin with the law of superposition. Now, I'm going to talk more about the law of superposition in a later episode. In fact, I'm going to talk more about all of this in later episodes because you can really dive deep into it. It's really interesting and important stuff. But the short version, the law of superposition, says that sedimentary rock units are laid on top of each other. So the thing on the bottom must be the oldest. The thing on top of it got laid down after it. The one on top of that got laid down later. You can't get, if you got a whole bunch of rock units, you can't get a young sedimentary unit, laying down a bed of sand underneath your rock units. It doesn't work that way. Now, there are always exceptions to all of the laws in geology, but law of superposition generally holds true in most circumstances, as long as you're not dealing with igneous, intrusive bodies. So if I draw a quick diagram up here, if we ignore what the symbols on these actually mean, because I just randomly assigned them here, and just assume that these are all sedimentary units that are, various kinds of rock. The one on the bottom is the oldest. The one on the top is the youngest. The one in the middle is somewhere in between. That's relative dating. Now, there is a major exception to this that I'm not going to talk about very much here. It happens very rarely, and I will talk more in depth about it in an episode talking about some of the creationist arguments about the age of the earth and how valid or invalid they are. I myself used to be a creationist with a pretty popular website way back in the day. I am no longer a creationist. So there might not be anybody more qualified to talk about it than myself because I've been on both sides of it. I understand the arguments in and out. But you do get out of place rock units in some places. And the short version of that is folding. So sedimentary units can be folded with tectonic stress. Your units can be squeezed accordion style and folded up. And there's no limit to how much folding rock can undergo, really. It just depends on how much tectonic activity there is in the area and how old the rocks are. But they can be folded up from multiple directions. You can get three-dimensional structures. You can have a fold like this, and then some tectonic action that pushes it up over here and drops this side down over here. Maybe you have some mountain uplift over here and a basin forming over here and a monocline forming. And then your rock units get tilted like that. And excuse the drawing, I'm a poor artist. But then when, folks look at the rocks, they say, hey, okay, so youngest rock, oldest rock, younger rock, older rock, younger rock, they're out of order. Well, we know why that is. It's been, jumbled up and tumbled around in a complex tectonic regime. That doesn't happen very often, but it does happen. And I mention it because there's always somebody who's like, there's a place out in Idaho where the rocks are all out of order. There's a place in the Grand Canyon where the rocks are all out of order. Well, they don't happen very often, and we know why it does happen in those places. We can map that. You have to look at the big picture. You can't just look at one spot. You got to look at the whole region and see what's going on. All right. Next, we have the law of cross-cutting relationships. Now, what does that mean? Well, we had our law of superposition. The law of cross-cutting relationships says that if there's a rock body that cuts into another one, the one that's cutting in must be the younger. How does that work? Well, let's take a simple situation where you have a fault and we have our rock units and we have a fault going through them and they are now offset. So, all right, so the law of cross-cutting relationships says that this fault must be younger than all of these rock units. Does that make sense? You can't have a fault cutting through rock units that did not exist at the time that the fault happened. And if we have a sedimentary unit up here that the fault does not cut through, now we know from the law of superposition that this unit must be younger than that fault because that fault happened before this one, it didn't cut through it. All right. If the fault happened after this unit was here, it would continue up through that unit. Actually, the way I've got this drawn, it looks like it's going partly through the unit. If that were to happen in real life, you'd know that this unit here and that fault are the exact same age. They occurred at the same time. I mean, not same age down to the day, but same age down to the same, period of 1,000,000 years or 100,000 years, something like that. The same is true for other intrusive bodies like a granite. All right. If a granite gets intruded, let me use a different color for my igneous stuff. Let me take out our fault here. All right. If we have a granite that's been intruded, again, the symbols don't mean anything. I'm just trying to differentiate them, the rock units. I'm not saying that this is the same as that. So our granite is intruded into this rock. What do we know? Well, we know that this granite must be younger than this rock. If this granite was older than that rock, then it wouldn't have been intruded into it, right? There wouldn't have been any rock unit for it to go into. Likewise, if there was a dike, which is a sheet of magma that comes up from another magma body, and if that dike were to come, up through here, we know that because that dike cut through here, same deal as with the fault, the dike is going through the granite, the dike is going through these rock units. It stops here at this one, so we know that the dike is younger than these rock units, younger than the granite it passes through, but it must be older than this unit up here because it didn't cut through it. That's the law of cross-cutting relationships. And these are all ways to get a relative age for the rock. This was incredibly important in the days before absolute dating techniques that we're going to talk about in just a minute, like radiometric dating. So you couldn't say, okay, this unit is, X million years old, but you can look at these and look at how they compare to other rock units around the world that might match up and might actually be the same rock unit, and you can get relative ages for things. So without necessarily knowing the age of something, you can be like, well, this is older than this, that's older than this, and that's how we ended up with the geologic timescale. Even before we knew the dates associated with them, we could say, all right, well, this is from the Cambrian period, this is from the Devonian period, this is from the Quaternary. There is one more very useful technique in relative age dating, and that is the use of index fossils. Now, index fossils have to be used in conjunction with absolute age dating. But in a lot of rock units, the rock isn't appropriate to radiometric dating or other techniques where you can find the exact age. In fact, almost all sedimentary rocks cannot be radiometrically dated. You cannot absolute age date most sedimentary rocks. There are exceptions to that. But generally speaking, if you have a sandstone somewhere, you can't take a sample, send it off to the lab, and they come back and say, well, this is 38.9 million years old. It just doesn't work that way. There's science behind it, and I'll talk more about that in a later episode as well. But sometimes you have fossils of organisms that spread out across the globe, were found almost everywhere, lived briefly, and then died out. They were just a flash in the pan. Sad as it is to say, human beings, the way it's looking, are likely to be a future index fossil. All right? It's not looking promising for us. But we are global. We are absolutely everywhere. And after we're extinct, the walking dolphins that take over the globe, who knows what happens. Future geologists will look back and be like, well, the humans left their mark. We can date everything based on the human remains. But we ourselves, we use things like ammonites, trilobites, spores, and pollen. There's all sorts of index fossils that can get a global spread. And they may have only existed for 1 million or 2 million, couple million years. And so if you see that species in your rock, so for example, if we find in this unit here, there's a little trilobite thingy. It's going to look like a mushroom because I cannot draw. Oh yeah. And this particular species of trilobite only lived from 310 to 300 million years ago. Well, now you know that this rock unit is 310 to 300 million years old. This rock unit is less than 300 million years old. This rock unit is more than 310 million years old. Relative age dating. Now let's talk a little bit about absolute dating. There are a couple of different absolute dating techniques. There is luminescence dating, which is something I'm not very familiar with. It seems to be growing in popularity. Very useful for more recent materials, and it's very, very complicated. It's something I didn't even learn about in school. But basically, sedimentary materials and things on the surface, well, they take damage from natural radiation in the rocks and various other processes when they're buried underground. But when they're exposed at the surface, strong exposure to light or heat kind of acts like an etch-a-sketch, where fission tracks through the quartz crystals have left their marks, just like you're drawing in an etch-a-sketch, and then strong UV light comes in and erases it. And so it's real handy for dating artifacts that have been buried. You can find out how long it's been underground. And sometimes you can find buried surfaces and figure out how old the soil is, things like that. There's also paleomagnetism. And that is a more intense study. It can be applied to very, very old things. And the basis for paleomagnetism is that magmatic rocks, lava flows and such, they tend to have little magnetite crystals in them, little bits of iron that like to magnetically line up with magnetic north. And so if you know the rough age of various flips in the North and South Pole, and Earth does flip its North and South poles regularly, then you can take a look at which direction the iron crystals in your lava flow are pointing, and get an age based on that. Real interestingly, we didn't really know much about the mid-ocean ridges or anything going on in the Atlantic Ocean. We didn't even know about tectonics really during World War II. But during World War II and just after, during the Cold War, the United States rushed to map all the seafloor. We needed the seafloor maps so that we could, send submarines out without having them crash into underwater oceans we didn't know about. And when they did those magnetic surveys, they discovered something crazy, that there's these vertical stripes all running along the seafloor that show the age of the rocks basically, and show the seafloor spreading. It was one of the strongest evidences we ever had for plate tectonics. And after we saw those magnetic images, there's really nobody who could be like, oh, tectonics isn't a thing. We knew, that was our smoking gun. There was a lot of evidence before that. After that, we're like, well, you got to be blind and put your fingers in your ears not to believe this is happening. But let's talk about radiometric dating, and that is a whole topic for another episode. We will go into that in depth later, but here's the broad overview. The basis for radiometric dating is that radioactive materials decay at a predictable rate. Every radioactive element and isotope decays at a different unique rate, but it's predictable for each individual isotope and element. Now, you cannot predict when any individual atom will decay. It is completely random. There's no way to predict that. But when you get millions of them together, those random events all combined to be relatively predictable. And let's talk about that because that might be confusing to you. All right, let's say we have an element, cragtonium. I'm giving it the symbol Cr. I think that's chromium, but let's just say it's cragtonium, named after me because it's a very unstable element. And it decays by producing a very energetic beta particle and becomes its daughter element, sophinium. All right, so we'll say the decay rate on cragtonium is 3 years. And that's the half-life, okay? So the half-life is 3 years. Now, I have a big pile of cragtonium in a box. All right, so in this box, I've got billions of cragtonium atoms. If I watch a single atom of cragtonium, there's no telling when it's going to decay and release its beta particle and become sophinium. It might decay in the first millisecond I watch it. It might decay after 3 years during the half-life. It might decay in 24 billion years. We just don't know. But we know that in 3 years, half of these cragtonium particles are going to be sophinium, and the rest cragtonium up here. And in a further 3 years, half of the remaining cragtonium will become sophinium. And in another 3 years, half of those will become sophinium. And in another 3 years, half of those will be sophinium. So you can see the way it's decaying. And so if you take a look at this and you say, okay, well, let's see, half, 3/4, 7/8, 15/16. So 15/16 of my sample is sophinium, and 1/16 of my sample is cragtonium. Then we know that it's undergone 1, 2, 3, 4 half-lives. So we know that it's 3 times 4, 12 years old. That's radiometric dating. Now, there are lots of different materials that can be used for radiometric dating. C14 is something that people are pretty well familiar with. There's uranium dating and several varieties of uranium dating. There's all sorts of isotopes, rare earth elements, unstable isotopes that occur naturally on Earth. But not all of them are suitable in all cases. There are lots of problems when you try to apply carbon-14 dating to very old samples because carbon-14 has a short half-life. I don't remember what it is. I'll put it up on the board. But, you know, if you try to extend it to something that's 400 million years old, well, there's so little of the original C14 left that any errors in your measurement are going to wildly throw off all of your results. And so you can't use it in that case. And of course, C14 dating is only useful in cases where something has been consuming carbon. So if it's a magmatic rock, you can't carbon date it. And this will be another topic we discuss in depth when we talk about creationist arguments. Often they'll be like, oh, well, this lava flow in the Grand Canyon was dated to only 6,000 years ago. Well, that's great, but you can't use carbon-14 to date lava flows, so who cares? And there are other things. You've got to be smart about making sure that you're accounting for all the potential errors in your carbon dating. One of my favorite stories was they were carbon dating the pelts of fur seals, I believe in the Antarctic. And they were finding ages for these fur seal pelts that they knew were a couple of hundred years old, but they're getting dates of like 100,000 years. And that's crazy. Well, it turns out you are what you eat. And the fur seals weren't out eating, grass on the surface. They were diving deep under the ocean and eating mollusks in places where it takes 100,000 years for the carbon that comes into the atmosphere to filter down. And so the age dates were all wildly off because the mollusk dates were incredibly off because it takes so long for the C14 to reach them that almost all of it decays before it reaches them. And then the fur seals ate the mollusks, and now you radiometrically date them and you're like, oh, the seal that died on Thursday is 100,000 years old. Well, no. And people who like to try to, find conspiracies and poke holes into science and be like, oh, it's an example, it doesn't work. Well, it works when you're smart about it and you understand what you're studying. We know the age of the Earth because there's one uranium isotope, I don't remember off the top of my head, I'll put it right here, has an incredibly long half-life of over 4 billion years. And so we can measure the amount of uranium locked into zircon crystals in the oldest rocks on Earth to determine how old those rocks are. But we can also measure the uranium locked in rocky meteorites that formed at the same time that the solar system was forming, that have been floating around since the formation of the planets, and get the age of those meteorites. And we say, well, those meteorites formed 4.5 billion years ago. Guess what? That's the age of the solar system. That's the age of the planet. That's the age everything came together. Now today, when we get the age of rocks, we often use a combination of techniques. And so I want to give you an example right now. Totally made up, but it's a great case study example. All right, here's my complicated example. We have a whole series of rock units here. On the top, we have a ash bed, volcanic ash. Beneath that, we have a sedimentary layer, another sedimentary layer, another sedimentary layer, and a lava flow. And then cutting through some of that, we have this dike. Well, what are the ages of these rocks? Well, I've got good news. You can radiometrically date most ash flows and most lava flows. And so we have an age on those. All right, so we have radiometrically dated our ash bed, and it's 300 million years old. We've radiometrically dated our lava flow, and it's 350 million years old. So now we know that B, C, D, and F will be our dike that I forgot to label. Here we go. Are all older than 300 million years old and all younger than 350 million years old. But I got news for you. In sedimentary unit C, you have been digging around for fossils and you discovered a variety of trilobite that looks exactly like a mushroom. And that trilobite is known to have only lived during a short period from 325 to 320 million years ago. So we know that this unit is 320 to 325 million years old, which means now we know that this unit is what? It is 300 to 325. Oh, sorry, 300 to 320. Boy, I'm messing that up. There we go. Million years old. And that this unit right here is 325 to 350 million years old. Now, we might be able to pin down the ages even further by radiometrically dating the dike. But we ran out of funding. And so, what age are we going to say the dike is? Well, we can use our relative dating to say, okay, well, we know it is older than 320 million years, but younger than the 300 to 320 million year old rock. Well, what age do we assign it then? Well, we don't actually know the age of B. We have a range of dates. And so it could be 300 million years old. It could be 320, but we have to err on the side of caution. So we're going to say this rock, this dike that cuts through could be as young as 300 million years old. And it could be as old as 320 million years old. It's going to have the same age range as the rock unit that overlies it, because we don't exactly know any more accurately than that, and we don't want to just make things up. A lot of people think scientists just make things up when we don't know, and we don't. That's why we give ranges of ages like this. Now, someone else just released a study, and they discovered that your sedimentary unit D in a whole other part of the world, maybe, 400 miles away, it's a very extensive unit, exists over here. But the units that overlie it and underlie it are different. In this area, D was deposited in a more volcanic environment. Now, of course, it was deposited in a volcanic environment here because it's on top of a lava flow. But here, there is an ash bed directly on top of it. And that's been dated to 330 million years. And somewhere deep down beneath this sedimentary unit D, a granite was deposited. Well, I won't say deposited, was intruded. Okay, since that edit, the diagram has changed very slightly because even geniuses make mistakes, and I edit. But intruded somewhere down deep beneath D, there is a granite unit, and that granite unit has caused metamorphism all through here, but there is no metamorphism going on in unit D. The metamorphism comes right up to the boundary of unit D, but unit D is not metasomatized at all. So we know that this must have come in after all the craziness here happened. Well, this granite was intruded 340 million years ago, radiometrically dated. So now we know that D must be between 330 to 340 million years old. Which means we can now go back over here and refine our ages. Now we know that this unit is 330 to 340. And this is what scientists are doing all the time. They're comparing the ages they have for the rock units, seeing how they align with everything else, and trying to refine their age estimates as much as possible without introducing any error. It's a complex system, but it works. And this kind of age dating has revealed pretty much everything we know about the history of the planet, or at least assigned ages and rough dates and age ranges to everything we know that happened on the planet. So, the answer to the question, how do we know how old rocks are? Well, relative dating, law of superposition, law of cross-cutting relationships, biostratigraphy, those are index fossils, and absolute dating techniques. Sometimes paleomagnetism, sometimes other more unusual techniques, but generally radiometric dating. And to do radiometric dating, you have to use the right tool for the job. You've got to use the right isotope. You've got to make sure that there's nothing that's going to screw up your data and give you bad ages. And there's plenty of things scientists have to control for a lot of variables. But that's how we do it. I hope that explains a lot about what we know about the Earth. Join me next time, and I promise there'll be a number of episodes where we take a deeper dive into all of this. It's really cool stuff. I think you'll enjoy it.